Assalamualaikum warahmatullahi wabarakatuh. We will present about our project assignment, and the topic is about simulating intermediate building blocks of a computer using logic gates in Logisim. For your information, we choose question 3 and 4 for this project. Firstly, the project is about illustrates how fundamental computer components are designed and tested using logic gates in Logisim. Our computer operations are based on basic digital logic, where small logic circuits are combined to form essential components such as adders, multiplexers, decoders, and registers. Logisim provides a visual platform for designing and simulating these circuits, which helps in understanding how individual logic gates work together to process data. The objective of this project is to develop a practical understanding of digital logic and the basic working principles of computer hardware.
This slide will be analyzing the design and function of a 2-to-4 decoder with an enable input. This is a specific type of digital combinational circuit. Its primary function is to convert two input bits, designated as A1 and A0, into four unique output lines, which are labeled Y0 through Y3. Crucially, out of these four outputs, only one line will be active or high at any single moment. The specific active output depends entirely on the current input combination of A1 and A0. The most important control mechanism for this circuit is the enable, or EN input. This input determines whether the entire decoder is active or inactive. If the EN input is set to 0 or low, the decoder is immediately disabled, and all four outputs will consequently stay low. Conversely, if the EN input is set to 1 or high, the decoder becomes active and will respond immediately to the signal present on A1 and A0. The circuit's operation relies on standard logic gates. The two NOT gates, which are also known as inverters, are responsible for generating the complement of the primary inputs, yielding A1, which is not A1, and A0, not A0. The four AND gates form the core logic of the decoder. Each of these AND gates is designed to check for one specific combination involving the input and the enable signal. For example, the logic equation for output Y0 is represented by the term EN A1 A0. I will now visualize the operation by examining the circuit diagram and its corresponding truth table. The circuit diagram illustrates the physical configuration of the decoder. You can observe the three input lines EN, A1, and A0 entering the circuit from the left side. It is important to note that all four AND gates receive the enable signal directly. This common connection ensures that if EN is low, the output of every AND gate is forced low, thereby disabling the entire circuit. The connections to the AND gates determine the specific output. The top AND gate is for Y0 is connected to the complemented inputs A1 and A0, while the bottom AND gate is for Y3 is connected to the uncomplemented inputs A1 and A0. The first row of the truth table clearly demonstrates the disabled state. When the EN input is 0, the output for all four lines Y0, Y1, Y2, and Y3 is 0. We will now focus on the active state, which occurs when EN is set to 1. When both A1 and A0 are 0, the top AND gate is the only one that can fire, resulting in Y0 turning on. Subsequently, if A1 is 0 and A0 is 1, only the second AND gate is activated, causing Y1 to turn on. This pattern continues up to the final input combination of 1, 1, which activates the final output line and Y3 turns on. The circuit serves as an efficient device for translating a simple 2-bit binary code into a unique single active output line. The operation is strictly conditional on the enabled signal being active. Decoder of this type are essentials component used in digital systems for tasks such as device selection and memory addressing.
This diagram shows a 4-bit register with load and clear, which is small memory circuit that store 4 bits of data. Each bit is stored in a flip-flop, and before each flip-flop, there is a multiplexer that decides what value will be stored on the next clock edge. When the load signal is active, the multiplexer selects the external inputs D3 to D0, so the register loads new data on the rising edge of the clock. When the load is inactive, the multiplexers feed back the current outputs, allowing the register to hold its previous value. The clear signal resets all flip-flops to 0, forcing the output to be 0000 regardless of the input. Together, this design allows the register to store data, update it synchronously with the clock, or reset it when needed. The circuit represents a 4-bit register with load and clear, built using 4D flip-flop for one each bit from Q3 to Q0 and multiplexer in front of each flip-flop. The multiplexer controls whether the register keeps its current value or loads new data from the external input D3 to D0. When loads equal to 1, multiplexer select the external inputs, and on the next clock pulse, the new 4-bit value is stored in flip-flops. When load equals to 0, the feedback path is selected, so the register holds its previous value even though the clock is running. The clear signal is asynchronous, meaning when clear equals to 1, all outputs are immediately reset to 0 without waiting for the clock. Overall, the clock controls when data is stored. The load signal decided whether to update or hold data, and the clear signal reset the register instantly. This truth table explains how the 4-bit register behaves under different control signal. When clear equals to 1, the register is asynchronously reset, so all output becomes 000 immediately, regardless of the load or clock. When clear equals to 0, the register operates normally. If load equals to 1, and rising clock edge occurs, the register performs a parallel load, meaning the next state Q T plus 1 become the input data D3 to D0. If there is no rising clock edge, the output does not change. When load equals to 0, even on a rising clock edge, the register holds its previous value QT. In short, clear has highest priority, the clock edge triggers update, and the load signal decide whether new data is stored or the old data is pre-reserved. Thank you.
So the challenge for 224 decoder is correct wiring of NOT gates and AND gates. Then the second is ensuring the enable input disable all outputs when inactivate. The third to verify only one output is active for each input combination. And the challenge for the 4-bit register or setting up the MUX feedback loop to hold the data and ensuring load signals select the correct input. Then making sure flip-flops update only clock pulse, and lastly wiring the clear input to reset all output immediately. But there are also some shared challenge which are testing all control signal correctly, then identifying and fixing wiring error, and lastly keeping the circuit laid out, organized, and easy to debug.
So in summary, this project focuses on building and testing key digital circuits in Logisim, including a 2 to 4 decoder with enable and a 4-bit register. The decoder demonstrates how basic logic gates such as NOT and AND gates work together to activate one specific output based on the input combination and the enable control. The 4-bit register shows how D flip-flops, multiplexers, load controls, clock signals, and a clear input are combined to store, hold, and reset data. Throughout the project, challenges include wiring the gates correctly, ensuring control signal function properly, and maintaining a clean and organized circuit layout. Overall, this project helps develop a practical understanding of how simple digital components interact to form important building blocks of a computer system. I think that's all from us. Thank you.